I'm really pleased to be able to present this project about ammonia fuel for aviation. That was the joint project between Reaction Engines and the STFC. Today I'm going to tell you a bit about Reaction Engines in case you don't know much about us, go through the motivation for the project itself, how it was set up, what we learned doing it, and what could come of it in the future. So Reaction Engines, as a company, is about 200 people. We're based in the Cullum Science Park, just down the road from Harwell. And the core of our focus is on this engine called Sabre, the synthetic air-breathing rocket engine. And that engine is designed to be able to take off from the runway up to Mach 5 breathing air, and then transition to a pure rocket mode to reach space. And at the heart of this is some really advanced heat exchanger technology, which allows this sort of engine to be possible. Now, that same heat exchanger technology could find spin out in a number of segments. One place we're looking at quite actively is high-speed flight, which is a really popular avenue for potential future applications. Another big avenue for it is anywhere where you need thermal management. So that could be in aviation, it could be in automotive, it could be in energy generation. The heat exchanger technology we've developed could offer a step change in performance in any number of applications, and that's actually really how this project came to be in the first place, really. Now, why do we want to look at aviation and zero carbon fuels? Well, because getting aviation to net zero is a huge challenge, and a challenge we have to meet. The UK is committed to net zero by 2050, and that includes aviation. These charts from Sustainable Aviation, published in March of 2020, show one potential path where you're looking at the effect of carbon price on demand, improved operations, fleet upgrades, sustainable fuels. But doing all those things, you still have to have some kind of market-based measures to get to a net zero solution, which is certainly a possible way of doing it, but it's a bit of really accounting sleight of hand to show that someone else is effectively not emitting on your behalf. If, on the other hand, you could find another route to decarbonizing aviation that didn't require that, you would have a very compelling thing on your hands. And that's what ammonia could possibly give you. Ammonia offers you a route to zero carbon air travel that is quite cheap. If you look at this chart on the right, it's from the International Energy Agency. These are the near-term and long-term, so 2030, 2050 timescale production costs for green hydrogen, ammonia, and synthetic aviation fuels. And you can see ammonia is actually very cost competitive. But it's cost competitive for more reasons than just its production costs. Ammonia has a pre-existing infrastructure, and as we'll show in a few slides' time, you don't actually necessarily need to change as much about your aircraft or your engines. And that means potentially you could also do these changes to a green or zero carbon aviation system in much less time than other systems might need. That's also aided by the fact that there's an existing ammonia infrastructure. 1 to 2 million tons of ammonia are loaded and unloaded off of deep sea going ocean vessels every month as they ship it around the world. That infrastructure is safe. Despite ammonia's toxicity, we've been handling it as a species for more than 100 years without major incidents. It's also a remarkably low fire risk, especially relative to something like jet fuel. And that's actually one of the main challenges of using ammonia in an aviation context, is it's not easy to burn. But if you can get it to burn, you're left with a fuel that has zero carbon, which means zero CO2 and zero soot emissions. There's no sulfur in it to create sulfur oxides. And, well, it is a nitrogen-bearing fuel. It is possible to burn ammonia without generating a lot of NOx emissions. And ammonia itself is used to scrub NOx emissions. So you have the potential, using ammonia, for a true zero-emission aircraft and engine combination. So this project was set up to investigate how that might look. And so the four main goals were to see how we could take Reaction Engines, thermal management technology, and STFC EnergyTec's catalyst technology to make a zero carbon aviation system. So within this was four main goals. One was looking at how that system would look thermodynamically and physically, both at an application and demonstrator scale. Apply Reaction Engines' heat exchanger technology to the vagaries of using ammonia as a working fluid to take heat out of a jet engine's exhaust. We explored how reactors could be set up to use the STFC's catalyst technology, and we also investigated how that catalyst itself performs at elevated pressures, which is something that hadn't been done before. And the results were very promising. The catalyst performance at pressures up to 5 bar, which is how high we could go during the scope of this study, were showing equal or better performance at elevated pressures, which is really intriguing behavior and something we're keen to explore more. Heat exchange and reactor designs were explored particularly for the demonstrator scale, and we showed that we could develop heat exchangers. Some of them are shown in picture form on the bottom right hand side of this graph, and they show really good low pressure drops, which is what you need if you want to integrate them into the exhaust of a jet engine. Cycle-wise, we showed that existing turbofans can burn an ammonia-hydrogen blend with only minor changes to the engine architecture. So if you have a cracking reactor that can give you something like 30% of the ammonia cracked into hydrogen and nitrogen, you can use the exact same turbo machinery, which means all you need is a new combustor and new heat exchangers, which is much less than a brand new engine in terms of development cost and time. We also looked at the impact of using a cycle like this in an aircraft similar to an A320 and showed that it could fly in the neighborhood of 2,000 kilometers, a little bit more actually, which is enough to cover the vast majority of the short-haul aviation market today. It's also potentially feasible to integrate this sort of jet engine concept with burning ammonia with a ammonia-based fuel cell to come up with a hybrid electric propulsion system, which would give you much better range than even this would give you. And the way such a system like this could work is you would have ammonia, which when you chill it to about 200 Kelvin is actually very similar to kerosene in terms of its density, which means it can be stored in wing tanks. That ammonia could be taken from the wing tanks and pumped through heat exchangers in the exhaust of the jet engine, taking some of the heat that would otherwise be dumped overboard to heat the ammonia up to a temperature where when you put it in the presence of catalysts inside a reactor, it cracks readily into hydrogen and nitrogen. That hydrogen and nitrogen ammonia blend could then be burned inside the engine, and the main byproducts would be nitrogen and water vapor. So it's a really promising architecture for future aircraft systems. And that's really one of the big takeaways of this is actually something that could be done feasibly, and it could be done quite quickly with the right funding and the right motivation. You could see aircraft fueled by ammonia flying by 2030. That's perfectly technically possible. And that's largely driven by the fact that you don't have to reinvent the aircraft or the engine in order to do this. But beyond aviation, the sorts of technology, the reactor and heat exchanger technology, would have wider application in a future zero carbon economy. So it could be used in any number of industries. And a great place to test a lot of these technologies could be something like the Net Zero Living Laboratory Harwell is trying to get set up. So with that, I'd like to thank you for your attention.